The first thing we look at is the feed-forward compressor. And what I'm going to do is I'm going to build the simplest possible compressor first, and then we're going to look into details, different components, how we can mimic certain things. Right, so audio input. For audio input I have this beat going on. Shit. Am I going to compress that, yeah? Let's make sure that it's a bit overdriving like that. Okay, that's better. Okay. So for now, nothing. That's it. Cool. So in making this compressor happen, what we're gonna do is take the audio input, yeah, and take it into the VCA, voltage control amplifier, which will be controlled. So the amplitude of the signal, the gain, is controlled by the signal itself. You see, so that's this crucial thing to understand, that the signal is going through an amplitude follower, and then we're going to condition that control signal. So this is actually the side chain. So we're going to season that signal such that it's suitable for VCA. So very simply put, the actual thing that we are looking for in this signal, so the bottom signal going up to the VCA, what we really want from it is to have a fixed offset, which would be kind of gain. There is some gain in the VCA, in the amplifier. And then what we want from this signal is to dip a little bit where the signal gets very loud. So that's the kind of understanding which is crucial to start with. So we have a gain signal which is dependent on the input audio signal. When the input audio signal is loud, then the gain signal dips a bit, and thereby dips the gain of the audio. Yeah, that's the thing. So obviously in an analog circuit there should be no real lag. It really depends on the amplitude follower in terms of how fast it catches the things, but we'll deal with that in a second. Okay, so to do that, first of all, let's get the sound into the VCA. And let us look, because I'm going to first do the simple thing, yeah? Because I have here this external input control, and what happens is that it gives me an envelope follower already. Okay, so the top signal there is my envelope already, and it sounds a bit like, oh, I didn't do that yet. Let's patch it back into listening. Okay. Would that work? Okay. So you see, this is the audio signal, and this is the amplitude follower signal arising from that. Yeah? Now, in a bit, we will also look at building our own amplitude follower. But for now, let's stick with the simplest thing. Yeah, this is visible. You guys can see it from the back, yeah? Cool. So actually what I really need to do now is season this signal. So first of all, you see that now when the amplitude goes up, the signal goes up as well, so we need to invert it. Yeah? So the attenuators are the modules that do this. I mean, you could have potentially a module that is just an inverter, which would invert the signal, but what we normally get is a kind of attenuator, so I'm going to show you that. So I'm going to take this amplitude signal that you've just seen, and I'm going to use an attenuator on it. So essentially the attenuator, the way it works is that if you're on 12 o'clock dial, then it's zero gain. Right? As you increase this dial, you get actual positive gain, so you get positive multiplication. But if you decrease it below the 12 o'clock, then you get the inversion. Yeah? So there you have it already. Now when the beat goes, when the beat plays, then I get some kind of an inversion going on. Okay, and then this matrix mixer allows me also to provide DC offset. So what you see here, I'm now gone through the attenuator and I have a kind of a range control, how deeply it dips. And now what you see there is the DC mixer and DC signal. Well, actually I have it all in one module. So I can add or subtract DC voltage from this, you see? So it's the same signal, but I can scale it up and down. So just you remember this middle line here, so the middle of the top half is the 0 volts line. Yeah? So what I'm likely needing is a signal that sticks, it's always positive, so I can decrease this for a bit. It's always positive and it dips a bit. Okay? So let's now take that signal and control the VCA. Okay, so we're gonna keep monitoring the control signal there and just do this. So now if I increase the depth of this signal, well, there you go. It's a horrible compressor as far as sounding goes, but the principle is there. And obviously with compression the key is to keep it really subtle. Yeah? I mean, depends what you do. Yeah, is that cool? So that's your basic most build of the compressor. That took 5 minutes, 10 minutes. But now we can dig into deeper things. Now, first question. Can anyone tell me how will I make an expander from this? Can anyone tell me what an expander does to start with?
You want to be making the quieter part of the signals less present.
Yeah, exactly. So essentially the theory goes that you have upward compression and downward compression, which means that either you push up the lower values or you push down the higher, so this upward and downward compression. And same thing, you would have upward expansion and downward expansion. Yeah? So upward expansion would mean that the loud signals get even louder, and the downward expansion would mean that they get even softer. Can you, yeah, you can come here, sit down here, yeah? No worries, yeah? Okay, so, yeah, so we know what is an expander now. So how could we make from this an expander? Any ideas? Yeah, exactly. So actually what we need to do is just remove the attenuator from the circuit. Yeah? Because what I have is that the amplitude signal, it goes up when you have a louder audio. So if I use that very signal, if I take the amplitude signal itself into the VCA to control the amplitude of the gain stage, it means that when it's loud, it's going to make it even louder. Yeah? So let's see if that can happen. So what I'll have to do is obviously invert back the signal. So I'm taking it low, see? So now I'm getting humps for beats, yeah? And now I'm just doing the DC offset. Yeah? Do you hear it dropping a bit? Yeah? Compared to the compressor, which would be something like this. So now it's attenuated. Okay? That's the compressor setting. Okay, so now we already had something funny happen here. So what happens here, now I have an inversion going on, you see? But what's happening is that it doesn't sound like a compressor, it sounds more like an expander or gate. Why is this? Because I have the inversion going on, so I've shown you without the inversion it's a bit of an expander, but now with the inversion I still get this gating kind of effect. What on earth is going on here?
Is it because some of the signals dropping below the 0 dB line?
Oh yeah, exactly. So what I actually have here in terms of my VCA is called dual Bc Polarizer. And what it does is if the control voltage drops below 0, it starts amplifying again, but with inverted polarity. Yeah? So you see now I have a kind of a funny compressor gate at the same time, yeah, something like this. Because essentially what you get is that only the thing, so again the 0 line is here at the tip of the pen, halfway in the upper half. So you see all the signal that, all the amplitude values that hit the 0 line will be attenuated. Yeah? Let's see if I can work this. So what I can do is I can decrease the range of the signal. You see, if I go to the 0 line, it's attenuated. And then if I go negative, I get the gain back again. So what does actually then happen if I have my control signal on both sides like this? I mean, it sounds a bit like gate, but it's actually not. Can anyone use reason in order to come to a guess what on earth is actually happening when this, I mean, we know what's happening in terms of, okay, when the voltage is negative, it is amplified with inversion. If it's positive, it's amplified without inversion. But what does this actually mean for the audio? For this idea of upward, downward, compression, expansion, what is actually happening here? Can anyone figure? So what is happening, so if you just look at the signal, what this means is that if the signal is loud, you will get non-inverted gain. If the signal is very soft, you will get inverted gain. And in the middle amplitudes is where you're going to get gain loss. So it's a bit like a Smiley transfer. What we've done is that we've made the really soft things become louder, the loud things stay loud, but the middle bits are getting soft. Does that make sense? Because you have the signal, the control signal, the amplitude signal on both sides of the 0 line.
Why is that useful?
It's not that kind of course, this one, you see. I mean, it's an experimental thing. I mean, we're here as far as using basic compressors, as far as using basic synths, you know where to get these bits. I designed this course to be based on things that no one will ever tell you otherwise. You know, because, you know, it's a way of deeply understanding the electronics and you know, understanding the potential for experiments. I mean, as far as this beat goes, I'm not sure how meaningful this patch is, but you know, we are not making music here. We're dealing with electronics mostly. Yeah? Cool? Everyone okay with that? All right. So now we can try, while it's a simple patch as far as the amplitude follower goes, before we get more complicated, is the feedback compression. So let me just first make it actually sound like a compressor. So we need inversion and we need gain. Okay. Okay, so just for comparison, let's just see. This is the uncompressed, yeah? Can you hear that? Well, it's a bit louder as well, yeah? That doesn't help. Let's get the levels straight. Yeah, is this audible? I'm not very close to the speaker, so I can't really tell. Okay, so we've got a compressor running. So the funny thing about the feedback is that, you see, the difference is that I'm not taking the amplitude follower signal before the VCA, but I'm taking it after the VCA. Yeah? So in that sense, I'm making a feedback path, which means that actually I'm controlling the amplitude based on the signal that is already compressed. So I'm not looking at the audio signal before compression and then making a gain change based on that. I'm looking at it after compression. Yeah? So this has a different sound. You actually have, if you dig into compressors, there are designs which are just feedback compressor designs. The thing to know in terms of difference here is that it will let attacks through more easily. Yeah? Although, because it's an analog implementation, there is no delay in the feedback loop, so to speak. I mean, there is some through the cable, but it's really, really small. And the other thing is that it can be more unstable. Yeah, so you can get this effect whereby, you know, it's making it louder, but then it's too loud, so it's making it softer and louder again. You can get a kind of oscillatory behavior from this kind of compressor. Nevertheless, it is a very valid design. Okay, so remember how this sounds. I'm not even sure we're gonna quite hear the difference. So the only thing I have to do to change this is to say that my input signal, oh, this will actually be a bit tricky, I'm afraid. This is tricky because my audio input is my envelope follower. So we might not be able to do that. Let me just think, because I don't even have, I have this only on a big jack here. No, actually we won't be able to do it with this amplitude follower. We can do the feedback in a bit when we build our own. Okay, so we're gonna do the building of the amplitude follower in the second half. But before that, let us look at slew limiting. Okay, so this is the one that says, oh, we didn't look at the gate. Let's look at the gate first. So there's one that says feed forward gate. Okay, so what you see here, this is a basic kind of compression scheme, which actually, can anyone tell me what is the threshold for this compressor? Where does the threshold parameter come in here? Any ideas?
DC signal?
Not really, no. DC signal is more like a makeup gain. Okay. Make sense?
Yeah.
The funny thing is there is no threshold. Yeah? I like to ask questions like that. It is just continuous like that, you see, because with the threshold in a compressor, what you have is that below the threshold it is a linear transfer. There is nothing changing about the dynamics, and above the threshold it is compressing. Now in this case what we have, that it's actually constantly changing the gain of the signal. So it's not that clean. You could say it is constantly messing up the signal. Okay, right, so in terms of the gate, what we have is something slightly different, because what we do is we use a comparator on the amplitude follower. So a comparator is a little device, and what it does, it compares two voltages. And in this case, what we are comparing is a DC voltage against the amplitude follower. So it becomes the threshold. So with this gate, we are actually inducing a kind of a threshold control. And what we will have from a comparator is essentially a kind of a gate signal. So if we just listen to this beat, I can set the comparator. You see? So now I'm catching the more and more of the actual attacks. So as you see, now after the comparator, now I'm patched in after the comparator, what I have is essentially a binary signal, on or off. Either the amplitude is larger than the DC signal or it is not. That's what I'm having, okay? So in order to make a gate, what I have to do is make sure that when the beats are playing, then it is open, which means that I have a gain in the VCA, and when the beats are not playing, then it's closed and I have 0 volt for the VCA. And I can achieve that, sorry, that was Okay, so let's take the gate signal in there. Oh, it's the power. Okay. So that's it already. Yeah. So now I can actually play with this. I'm just straight from the comparator into the VCA. And what I have here again is this funny thing that if I don't dial into the zero line very precisely, then I will be getting the soft bits through. Okay. Now the thing is, you don't see the thing is that let me see, you're seeing the gate. You don't see the gate signal after I'm seasoning it, so I'll do it like this so you can actually see it. Give me a second, because again it's quite crucial to tune the control signal to what you would need. Okay, so this is now my CV signal, and this is my control signal. So you see I can actually drop it below the zero line. Is that kind of happening here? Sorry, we're watching the wrong signal. There it is. Yeah. So again, I have a way to offset it and to increase the gain. So now what we have, see, I'm trying to get the bottom bits straight on the zero. If I drop it below the zero, then I get a really funny effect, because what's happening now is that I'm playing, both the soft and the loud bits are playing, but there is a phase inversion. There's a inversion happening when the loud becomes soft and when the soft becomes loud. So the soft bits are inverted and the loud bits aren't. Yeah? Now this could be interesting, for example, in a stereo effect, which is not something I can build here. Yeah, you can imagine this, because if I have the lower ones inverted, then it would jump far off into the speakers. I get a widening effect. So I can have a kind of a widening compressor. There's a lot of things you can come up with, yeah? Okay, so we have this signal now, and let us now look at slew processing, okay? So you see it's a square type signal. Let's tune it back so it's a gate. I want to get back to the zero line as much as I can. Although it does sound a bit like, actually I'm afraid I'm compressing it, yeah? No one noticed? I think I'm doing it the other way around. This would be the gate. Let me see, there it is. Yeah, that's more like a gate, yeah? I can change the threshold here. All right, Mom. Okay, so now I've got this gate. Now let's look at this slew processing. So what slew processing does, it limits the flanks. Yeah, so it limits it in two ways. One is the upward, and the other one is the downward. So what it essentially gives you, what you're used to, is it is a attack and release control, yeah, very popular with compression. Okay, so I'm gonna patch that into my little slew processor, and let's see what it does. So what you see already here is that the down flank, you see, I can make it smoother. Now if I overshoot that, then it never really goes up anymore. So I can make the down flank smoother, or I can make the up flank smoother as well. Will that work? Except, yeah, there we go. Yeah? So it is a way of seasoning the signal to make sure that it doesn't have this radical drop. So let's see what that does. See? So now it's a bit late to catch the actual attack. And if I do it the other way around, if I keep this, so now it's catching the attack, but I'll make sure that it actually takes longer to drop. And increase the threshold for that. Let's see. Okay. You see, so now it has this kind of a little fade out after the attack itself. Yeah? Now the nice thing about this one, this Slew processor, is that it actually has a control over the curvature of the flank. Yeah? So what I can do is I can make it curvy potentially. I'm not sure how much we will hear from that. But in essence, what you can do is make this curvature. Let's see, that's exponential, sorry. Exponential. A bit more in there. Okay. So you see the curve of this decay there? And I can possibly turn it the other way around, you see? Or this way around. Yeah, it goes both ways. Now obviously I'm not really producing this beat at this stage, I'm just making it obvious what it does. So the trick in doing this well is in subtlety, which I cannot perform now. Okay, is that cool? So we got the slew limiter in there. Good. Any questions so far? Okay, so then what we can do briefly is just verify what we've talked briefly about last time, which is that every smoothing of a waveform is low-pass filtering. And every low-pass filtering is the smoothing of the waveform. So I have this really fancy slew processor here with the curvature exponential. Actually, it's voltage controllable as well. But the message is that we are trying to do unorthodox experimental things. So what I want to show you briefly is what will happen to this gate if I take the control signal through a low-pass filter. Yeah? So because let's take this one. We can try a few. I mean, obviously we're not in the situation to critically listen to it and tune it anyhow, really. Am I doing the right thing here? Did I just lose the... Just a second. Oh, the computer went to sleep? Oh yeah, it looks like this was unplugged. Okay, I'm just gonna grab that for a second because we need the sound for that. He's in the middle of the mix, obviously. But we could be able to make it. It's just that the power is Anyone got a phone with some beats on it?
My battery.
I have a charger. Yeah, it would help. Maybe he's just coming. I have no idea because it's not. Hey, yo, I have no idea. It doesn't light up the power. Did we check? It's all plugged in. Yeah. Oh, now it is. How was that?
It's just on the wall. Turn off.
Oh, it was off. All right.
There you go.
No password, I hope.
No, just here now.
Cool. Okay, we'll start that up in a second. Don't keep the door closed, yeah?
He's not coming back.
Musical environment, yeah? It's a bit less sterile than UE. There is a password. Or maybe it's just no password? Ah, it is just no password. Right, that should be better. Okay, so where were we? This is the input, this is the CV. Okay. This is my control signal.
I don't think Ava's was making a noise.
Yeah, it just stopped because I didn't look this sound file. Just look the very first one. Okay. Just gonna look, I hope. Sweet, so we've got audio out there. We've got our gate signal here. Okay. Right, and then okay, this is the offset. Is it again not making? Can you please play it? What the hell is going on here? Well, let's try the first one. The first one did play at least. Try to loop these as well, but it did stop. Okay. We get something? Yeah, we're getting it now. Okay, so back to where we were. Okay, so now we've got this funny thing, which is not even a gate. Okay, so let's make this a bit more radical. That's a bit like a gate, yeah? Okay, so what I'm trying to do now, I've already taken the slew limiter out of the circuit. And what I'm gonna do now is I'm gonna use a low pass filter to change this waveform. You see? So it's this kind of a square wavy thing. So let's see what the low pass filter can do to it. Bit softer, yeah. So what you see is obviously that, you know, it has become rounded, the whole thing, and it depends a lot on the resonant frequency. You see, because actually, if my low pass filter is completely open, I get this kind of response, and then if I turn down the cutoff frequency. So what you see here is actually that After the attack, I get a bit of a dip. So I get this kind of phase inversion happening in there. And what I could do, what might be meaningful, is to again season this signal a bit. So we again take it through scaling and offsetting. So that I can make sure that it's not so dramatic. So I can make a kind of a lesser curve in there. And the funny thing now is that I should be able to get some kind of interference with the bass. Yeah? So if I increase the resonance of this filter, this is a bad idea. Okay, so this one is off. Yeah, the message is that with the low-pass filter in this control signal, I can get quite a few things happening as well. We can try another one. Obviously, it's not the kind of environment where we can really tune it to be horribly interesting, but it is more about demonstrating the principle than making something crazy. At this stage, I can also take a bandpass filter. Let's see briefly how that works. So you've seen what these filters do in terms of response last time. Okay. So this is resonance. This is noise volume. Okay. So what you see with the bandpass filter, I get these spikes. Now if I play with the... So you can almost hear the bandpass filter through this. You see how it's doing the fuck sound? Because the funny thing here is that can we understand what's going on? So what happens if instead of just a basic control signal that goes up and down to control my gain, I start to get these oscillations in there? What happens to the spectrum of the incoming signal? Because what am I doing? I'm using this signal to control the gain, so I'm multiplying with it. So I am multiplying with something, let's say, at 200 Hertz. What happens if I multiply with the 200 Hertz signal?
More bands.
You get sidebands. Huh? So essentially what I'm doing with this, I'm getting these funny sidebands. I can try to increase the amount of this. Radical compression, yeah. Actually, it's still kind of gating, but that's the point, that you see that actually all of this dynamic processing is really kind of a rich experimental territory that can really reshape your sound. Yeah? And all you're really dealing with is a gain stage and a signal that is derived from the original signal. Yeah. Okay, so we're gonna slowly get into building different amplitude followers, and we have a really nice way to get there because of what we've just realized. You see, I've said that you multiply the audio signal with a signal derived from that audio signal, which is essentially a low-pass version of it, in a way. Yeah? So what would happen if I just plain multiply the signal with itself? And that's math. You should know this. You should derive this. Ben should know this.
It'll go very fast.
Yeah, what's happened if I multiply a sine wave with itself? What's going to happen?
Double the amplitude.
Well, not necessarily. It really depends on the scale of the things. When you double the amplitude, that's the addition. Yeah, when you add two things, then it doubles. But I mean, in the digital system, you see, if the sine waves are below 1, then multiplying two numbers which are below 1 will never yield a number larger than 1. So, and in an analog system, it really depends on the offset. But you see, if there is no exceeding the unity gain as such, then there should be no amplification. No? So it's not amplification that we're looking at. Trigonometry, guys, no one studies trigonometry. Actually, what you get is doubling the frequency. Yeah? If you just know the ring modulation, yeah, if you multiply with the sine wave, what do you get? You get two sidebands. You get the sum, you get the difference. Yeah? So now we're looking at the case that we're multiplying the same frequency sine wave, so you get the double frequency and you get the 0 hertz, because any number plus itself is the double and any number minus itself is the 0. So that's what you get. You get an offset signal which is twice the frequency. If you think about it from another perspective, what you have is a sine wave which is a bipolar signal, goes up and down. And what happens when when I multiply two negative numbers? It becomes a positive number. So that already tells you, okay, so as soon as this signal would want to be negative, as soon as the input sine wave goes negative, because I'm multiplying it with itself, it will stay in positive.
What inverts the signal?
So actually, technically, you get a clean sine wave. That's the funny thing, because you would think, okay, well, it's inverting, yeah, but actually, it's making the curvature in there as well, because of the square transfer, yeah. So and mathematically and really, you get a clean sine wave. So as soon as it approaches the 0, it will actually be smoothing itself out and coming back again, and it will be a perfect sine wave. Yeah. So sine wave multiplied with itself gives you twice the frequency sine wave and DC offset. Yeah. So in both ways, you can approach it, from thinking about multiplication of numbers and from just knowing the sideband theory. Yeah. Okay, so let's see that. Yeah, let's just see what happens if I multiply the signal with itself, especially because I've got a beat. Let's start with just a simple wave. Well, actually, in this track I don't have a sine wave, but I have a few other things, so we can probably have some fun with that. I will take a triangle wave, okay, and I'm going to multiply it with itself. So I'm essentially taking a gain stage and I'm feeding both the CV input and the audio input with this signal. Okay? That's not horribly informative. This is the, let's see, this is the original triangle wave. And actually I have to, oops, it just doesn't quite reach there. Use this one anyway. So this is the original, the one that you see, and then below is what happens after multiplying with itself. Okay? You see? So when it's wanting to be negative, it's staying positive, and it gets this curvature. If this was a sine wave originally, then I would have a perfect sine wave, but it wasn't. It starts from a triangle wave, so the top is still triangly, and that's what happens. Okay? Now that's the triangle wave. Now how about the drum beat? That's what happens. So technically we will get octaving effects. Yeah? The thing that we get as well is a lot of different sidebands and a lot of intermodulation artifacts as well. So that's why it's really dirty. Okay? Now, what I'm gonna do, just to make this a bit experimental at this stage, what I'm gonna do is I'm gonna low pass filter one of these signals. Yeah? I mean, technically, if it's a clean multiplier, which this one probably isn't, we should be testing for that as well in a second. So I'm gonna low pass filter one of these signals, which means that I will get less anomaly. Am I in the wrong range here? Oh, 5 volts. I'm really killing this. Okay, that's a low pass. Let's try a high pass. Because you see, this in a way is also... did I do the right thing here? Yes. Is this one alive? Hello. Looks like my filter is dead. Let's try this high pass. This is output, this is input. Now this one has the most gain, but this should give us something. So this is without the filter, output, input. So it's funny because this one worked nicely, yeah? For a second. Did we break something? 48. Well, in any case, you get the idea. We can process this signal in different ways, and actually doing this already. So this is kind of your unorthodox distortion, multiplying signal with itself, and then low pass filtering one of the halves. Because that's essentially what a compressor is. Because if you look at the graph, your amplitude follower is essentially a low pass filter, and this is where we're getting to now, into this amplitude follower business. So first basic amplitude follower is essentially well, we have two types. You have the peak followers, you have the RMS followers, and there's a lot of different ways to do this. The most basic thing is actually squaring. Yeah. So what is supposed to happen? So let's get this beat squared with itself again. Yeah. So what is supposed to happen here is that this is my top is my input signal, yeah, and then the bottom is my output signal. So what you see here already is that I've made this signal strictly positive. Yeah? Now, having done this, I've actually made it already slightly easier for my lagging is the slew limiting, yeah, to give me a decent amplitude follower signal. You see, because what I really want, if you imagine, I actually didn't even ask last time, you can sort of see this, yeah? So if I have, let's say, just a sine wave which changes in amplitude, goes up and down, something like this, So what I really want from an amplitude signal is to kind of connect the peaks. That would be my peak signal. I mean, from an RMS signal, I would want to essentially estimate the surface enclosed between the waveform and the zero line, which would have to do with the energy of the signal. But now I'm not, so those are the two things. Okay, so if I do my squaring, then what I get is that all the negative bits, as you see, will start pointing up. So this one will be up, this one will be up, this one will be up, and so on. So actually what I have is a better signal in terms of being able to get a smooth signal that connects the top. So it's the next step towards the connecting of the tops. So that's what I have here. I mean, at this stage, obviously it's a beat. We can't quite see how well this works. Let's see if we get into the detail. Oh, we won't really get there. We're not using analytical signals now. Okay, so after I have this squared signal, so now I'm building an actual amplitude follower. There is one which says amplitude followers, amplitude following 1 and 2. So I'm actually building the lower one. So you see, I take the audio input, I've squared the audio input, and now what I'm gonna do is I'm gonna take that signal through my Slew processor, through my lagging network, and I will make sure that we see two signals which are both informative. So we are losing the original signal from the top. Oops. No. So we lost the original signal from the top, and now we're gonna look at the signal after inversion. Whole lot of cables here. Okay, I will need another one, just a sec. Okay, so what we are trying to get is on the top, we want to get a lagged signal. I'm gonna take linear now. Let's see, we take linear down as well. Okay, so now at the bottom I have a clean signal from the squaring, from multiplying with itself. And then at the top I have this other one. Let's see if we can trace that. It's a bit loud, all of this, yeah. Let's try to see if we can catch that. Okay, and then I'm trying to make the signal smoother. Would that work? Yeah, you see, so the bottom one is the actual squared input, and then the top one is with some slew processing. Okay, so I'm lagging it. So all the kind of fast fluctuations are excluded from there. Let's see on a larger time base. You see? So from all of these, this is very high frequency signals. I'm actually losing those high frequencies. And I'm also losing a bit of gain. So now that I have this, what I really want to is season this signal a bit and make sure I have an appropriate signal to go into the gain stage. Okay. So here we are, and now I can offset it and increase the gain and invert it, although this increase of gain is not huge here. Okay, so this is so now I have inverted it, and I can offset it. So now essentially I've built my own little amplitude follower, yeah, from squaring the signal and then lagging it. And finally I'm getting into slew processing. So now what we can attempt to is listen to this in terms of a compressor. So I'm gonna get the input signal in, and I'm going to get this voltage control signal, and I'm gonna listen to that happening. I mean, not that we are in the situation to really hear a huge difference, but what should be apparent, well, this is not horribly clean, but fairly. But if I now take back the slew controls, you definitely hear the difference there. Compared to this. So what I'm doing is essentially making the control signal faster or slower. I mean, we probably can't hear it, but technically the downward slope. So now I can do this. So I've done this both for attack and release, increase and decrease them. So now it's the minimum attack and release. So I can try to increase the attack only. Okay, I'm back to the original, and now increase the release. And I can do again a similar thing. So instead of my VC processor, I can use a filter. See? So now I'm doing a very high frequency filtering on the control signal, essentially the square of it. Okay? So what I would like you to do now is draw this circuit, just to see whether I've lost everyone. Because we have a slightly more complex thing. So we are using the squaring amplitude follower. Yeah. But instead of the slew limiter, we are using a filter. And then you should insert this into the feed-forward compressor. Yeah? So you have these two things. Luckily, they're on two different papers. So if you're looking at amplitude following 2 and the feed-forward compressor, yeah? Can you combine the two and use a filter instead of the slew limiter? Okay, so let's have this as a break for me and a bit of a brainy for you.
Your pen?
I should have at least one. There you go. Anyone else needs a pen? You guys alright? Huh? You need one.
You've got one, I'll have it, yeah.
Thought I might have taken another one, but I didn't quite. Can you do with the screwdriver? Well, here's the marker pen, yeah? At least you can scribble something. Oh, you've got a pen?
I'm not sure if it still works. I have another one as well.
I have scissors here as well, so you can cut it out, yeah?
So I've just...
Yes.
Oh, I mean, all you said was replace the slew limiter with the H.
Yes, and insert
and insert that there.
Yes.
And then, but that's just a square and the H.
Yeah, the funny thing is that the squaring is also a VCA. So that's what we're gonna get to.
Okay.
Is the funny thing that actually I have two VCAs patched in here. Yeah. And also after the filter,
Yeah.
I have scaling and offsetting.
Oh, yeah. But you didn't tell us that.
Well, did you follow? That was my question.
So you're squaring the signal, filtering it.
Yeah, except there is no amplitude follower
No
anymore.
amplitude follower.
Yeah.
No attenuator.
Attenuator, yes, but not in that space.
Right, okay.
Yeah? It's probably best if we discuss it together. Let's see yours.
But you're saying that's not there.
Well, yes, after the filter.
Yeah, which there, yeah. Square filter. and
Square filter, yes.
Yeah.
But where is the square?
Yeah, that's
Okay, the square. Yeah, yeah. It's a bit like this. Yeah.
But you said there was something else that I was missing.
Well, the thing that the squarer is actually a VCA. So we should test for this, maybe that's the next best thing, to see whether it's a proper multiplication, bipolar and frequency independent. You see? Because it could be that a VCA, that's why it's important to, get to this level, because it could be that your VCA does not allow you to change the gain of the signal with a 20k, sine wave. You just never know. Some of these things have certain things. Yeah, so shall I draw one then collectively? Can I have the pen back? So the funny thing here is that I have two VCAs working. So I have the input signal. Okay, and then from this input signal I go into my first VCA, VCA1, and I go into there twice. You see, that's my squaring. So actually one of them is called an input and the other one is called a CV, but I'm using them as if it was a neat little multiplier. So
Sorry for the acid.
no worries, it's actually not that loud.
That's what that's just you having to do a setup, right? You could have, you can get multipliers, right? You don't need.
It's questionable. I'm not aware of having like a clean-cut multiplier. It's only VCAs normally. I mean, a ring modulator should be also a clean-cut multiplier, but that's the thing, we have labels and electronics, and the only way to know whether it's actually doing it is by looking at it. And I saw that it did indeed square my triangle wave, so I can assume that it's good. But actually, it's probably the best next thing to do is to take up the frequency and see if it breaks at some certain frequency, because that might be the case. I mean, do you know op-amp electronics like that? Mm-hmm. It's not really supposed to break, I think, at a certain frequency.
That's interesting. I hadn't thought of it.
I do have, for example, attenuator and offset kind of module, which breaks at 3K. It just doesn't allow frequencies above that. And you just never know what.
Yeah. But not all VCAs allow ring modulation, right?
Well, that's the question. Yeah,
I don't think they do they?
Probably not, maybe yes. I don't have many to test really.
Right.
I'm just suggesting you have to test it before before you assume anything. But I wouldn't know why this one would cap at 3K, but it does. It just stops transmitting the signal at 3K. Okay, so I go into my VCA twice with the input signal, which is something I call my amplitude signal. And then this amplitude signal, this is my square signal, goes into, well, I currently had a low pass filter. This one went into an attenuator and an offset. So I would say times something and plus something. And then this signal, so you see here comes in the second VCA. This signal goes into the CV input of the second CVA, and this is the audio input of the second VCA, and that's my output. Make sense? You can send it around. I don't know if it makes sense. Do ask questions. So that's the trick here, that I'm using my VCA to square things. And well, actually I do like the high frequency shit that this one is doing. Band pass. So you see, it already has a kind of It has a bit of a ring modulation sound to it, yeah? Well, I've lost all the gain now, but it's getting interesting. Oh, that was the wrong. Okay. Shouldn't have done that. This one was the bandpass output. Okay, so now I have a bandpass filter in the Slew Limiting role, increasing the resonance for that. You see, it's actually acting almost like a side chain filter. See? I like it. Okay. Right, so that's our first self-made amplitude follower right there. How about we test it? I'm actually curious. Let's see if it does the breaking at a certain frequency. So let us just take a basic triangle wave. Sorry, no sine waves today. We ran out of sine waves, yeah. And actually, none of the sine waves are really sine waves anyway, which is really funny. They're all quite dirty. Okay, so now I have this squaring, so I'm putting in a triangle wave into the both inputs of VCA. And this is the original, and then if I make it square, that's what it does. So what I can do is try to make this quite equal. Huh? Okay, so let's see. Increasing the frequency. Maybe best if we also hear it, because then we can tell if things start happening. Because obviously it's not only about whether it breaks or not, it's about how it breaks, and we want it to break as well. Very often we do. Okay. Yeah, I think it's safe to claim that this VCA does not have a frequency limit, yeah? Okay, the other thing that we should test, actually, if we really want to know what's going on, is the polarity. Yeah? So, what I will do, I have here actually two DC generators, which go between -5 and +5. You've seen it on Wednesday. So just to verify, yeah, this one goes +5, -5, yeah, and this one also goes +5, -5. So what I can do is, I'm not going to be listening to this. What I can do is send these two DC signals into my VCA in order to find out how does it respond. Now the thing is that I have, this is a Bc Polarizer, so it's slightly more complex because it allows me to polarize the incoming signal as well, meaning that I can multiply it with the negative value, I can invert it. Okay, so now I'm looking just at the output. Now this is -5, -5 into the output, and it is gone over the top. You see, I have two negative voltages coming in, and the output voltage is above +10. Yeah, which makes sense. Yeah, two negative numbers multiplied is a positive number. Now I will increase one of the signals going all the way up to plus 5 volts, and you see I get minus 12. Yeah, so I have a plus 5 and a minus 5 in there, and I get a minus 12. And now if both of them, so now the second one is going positive, now both of them are positive, I get plus 12. So I could say, well, it looks like polarity wise it works. Both of the signals can be negative, so now the second one is negative, and the second one is the audio signal input, and now the first one is negative. So both of them would take bipolar signals, which is a questionable thing. I mean, by design, maybe they design a VCA. Oh, you're staying here, are you? Maybe they design a VCA where you don't have a bipolar input for the CV input. You see, so those are the things that you typically want to check. Okay, right, so shall we now try and build a different type of rectifier, let's try to do different rectification. So I have actually two more ways of doing it with some basic modules. So let's get a triangle. Okay, multiply with itself, and then frequency goes lower. There it is. Okay, make it a bit softer. Yeah, that's a triangle wave multiplied by itself. That's the squaring of it. Now, the other technique to produce an amplitude follower, so now we're looking at amplitude following 1, is a full wave rectification, which is essentially the absolute value of the signal. That would be just taking the negative parts and turning them into a positive part. Now, this is not trivial. I bet there is a module which does full wave rectification just like that. It's not difficult to design in an actual circuit, but we have to make do with what we have here. So one of the ways I can do this is a voltage controlled switch. Okay, so let's introduce this beast. A voltage controlled switch actually works both ways, the one that I have here, 850. So it can either have one input to two outputs, or one output, two inputs to one output. Yeah? Because it's actually just a switch, it doesn't really matter which way you send things through, either two inputs or two outputs. Yeah? So it's a kind of a three-point thing. Okay, so what I can do with this, and the switch itself, so I have three either inputs or outputs, and I have a fourth CV control, which will, based on a voltage control, whether it goes one way or the other way. That's what's happening. So I can possibly demonstrate this. Let's get friendly with the voltage control switch. I'm gonna have two different frequency triangle waves, just to make sure that we know what's going on. Two different frequency triangle waves. I'm gonna monitor the output. Yeah, I see one of them. And then I will use my DC signal generator to control this gate. So if it is a negative signal, I had the previous triangle and now it's this triangle. So you see, when the tipping happens, I'm just switching between two triangle waves, yeah? And this is at 0 volts. Make sense? Okay, anyone can predict how on earth I'm gonna make a full wave rectifier out of this? Well, what you do is you take the same signal into the control input. So I'm gonna use this one triangle and use it to produce the switching. Yeah? And I'm gonna feed that triangle, which is doing the switching, into the input. And then what I have is two outputs. One of them looks like this and the other one looks like this. Now it's not horribly informative. Let me see if I can get the second channel in there. Just about. Oops. There we go. So what you see here is that this is what it does. Okay, this trigger seemed to work a second ago. Okay, that's better. So you see that the top part of the triangle is in one output and the bottom part is in the other output. Now you also see that there is a funny thing here. There is a kind of an overshoot as well. What I could do is, let's try to fix that. So I'm gonna... I wonder if I can fix it, but I hope I can, because I see in both cases it is just above the 0 line. So with a bit of offset I might be able to fix it. So I'm gonna take my CV signal through the offset, okay, and then full on, okay, and then now I'm changing the offset of the CV signal, so I can indeed fix it. So it seems just that this one needs calibration. So now I've managed to make that happen. Yeah. So now I have one which is a top and one which is the below, and obviously what I will do is I will take one of them and invert one of them and keep the other one intact, and then I should get my full wave rectification. So let's try and do this. So I'm taking both of these signals and mixing them. Make sure it don't affect this one, although it probably will, because I'm using the same matrix mixer. This can get funky. Okay, so now I am making sure that one is inverted and the other one is not, and I see already that it's not quite doing this thing. I'll have to try and make the peaks even. This one is much lower amplitude for some reason. That should be alright, should be alright. Oh, probably this, yeah. Okay, can I get that happening? There we go. Right. So that's my triangle wave through full wave rectification. Okay? So now comes the interesting bit, because now we don't do this to a triangle wave, but we do this to a to our drum beat. So goodbye triangle. This one, okay. So that should be. Is this still playing the drum beat? Yeah, it looks like. Okay. And then the blue is the listening cable. Okay, so now, before you blast your ears. Okay, so it looks like we have something. Did I manage to mess something up here? CV there. These two signals here. I bet nothing happened on that side. Okay. CV, oh yes, I did mess things up, so this has to be the input signal right there. Ooh, I think I messed up my patch. Getting a bit lost. Because this one was just there. This one was the input signal. Let's see this. And this one was derived from that indeed. Well, hopefully. So yeah, and now I have to figure out what am I listening to, so that's this combination here. And with the, there we go. Okay, so if you remember how the squaring of it sounded, you see it's getting dirtier, it's distorting, but it's not giving us the kind of octaving sound at all. Although it should. It definitely should. but that's what you get. I can change the ratio of these two things. I have some feedback options in here as well. Okay, so that's my rectification from a switch. Makes sense? I'm gonna get this one calibrated. Right, another type of rectification I can do it with the comparator. Yeah. So let's see if I can build that. So we're back to the triangle wave. And with the comparator, what I have is essentially a binary signal. So let me just try to demonstrate this nicely so you can see both the triangle and the compared bit. So this will be my triangle, and okay, and then below that compare. Oh, that's funny because okay, that's better. Right, offset. Gap goes down. Here we go. Okay, so that's my comparator output from this triangle. So you've seen something similar last time with pulse width modulation generation. So if I change the control signal value, you see I am actually getting the true-false thing happening in a different spot. So if I want to make a full wave rectification out of this, what I really need is a signal which is up and down for the same duration. Looks like it's going to take a bit of tuning. Here we go. Could play with the trigger of the oscillator to make that a bit more accurate. Okay, it's getting narrower, broader. Okay, so it's somewhere here. Does that look even? That looks about even. Okay, so what I've now got is a signal that essentially splits the triangle wave into two phases. So, and it should be lined up with the zero line, more or less. So what I can now do is take the same triangle wave, and I actually have inverted output as well. So what I can do is I can take that triangle wave into VCA. Okay, so that's the input, and then the control signal I will make from essentially balancing. Now actually I have to make two control signals, so I have to do this twice. Yeah, so I'm taking the triangle wave into two VCAs, okay? And one VCA will be controlled by the comparator signal, and the other one will be controlled by the inverted comparator signal. Okay, and now what I do is I mix these two up. And this should be my output signal. Okay, so it's still all over the place, likely. Let's see, full on this one, full on that one. Okay, one of them is not quite, so this one looks fine, more or less, and this one doesn't. So let's see, that's this one, CD, manual. Oh yeah, well the thing is that this one will zero it out. offset triangle in both. Okay, so it's only about making sure that these are well mixed. Okay, that's that one. The other one is quite a bit softer, but we can potentially get to the... Okay, so I'm sort of getting there. It's just that for some reason this one is much softer, yeah? Let's have them both full on. So maybe it's useful if I just look at each one separately, okay? So this would be one of them, and it's not quite inverted. Let's see. I think I have to do here with, so this is 0.5, same thing there. So I'm a bit messy here, let's see. And then this one. And so this is the sum, looking at the top one. The thing is, I think what happens here is because of the, it's not a clean VCA, attenuating one. I get a negative voltage. Okay, I think I can't do it with this VCA, unfortunately. But I have something that looks funky. Yeah. Let's listen to it, yeah, now that we're here. Anyone up for that? We can do an exercise to build a... Okay. So that's this waveform. It's not horribly exciting, but indeed, let's see. Here what I would actually need would be both positive, yeah? So this is now what I'm listening to. Okay. Still have a chance to get it. Okay. So one of them is doing funny things. There we go. Nicely anomalous. Well, I do get some kind of rectification, but I can't quite hack it. So, shall we try to sketch that? Yeah? Let's see if we can first hack it with our brains. Yeah? How do we make a full wave rectifier out of a comparator? Yeah? Pens? Beer? Yeah, so do we understand what the comparator does? Oh, hello. Nice and smelly back there. Yeah, so the comparator will give you a binary signal on or off based on whether the voltage is above a threshold or below a threshold. So it is a lot like in a digital, like in max MSP, the larger than. It takes continuous signals and it outputs yes or no.
So if you're larger than a certain thing, take whatever you're comparing to above that and you want to invert that signal to rectify it.
Yeah. Yeah. So we have a way of detecting whether the signal is negative
or positive.
Yeah. And what we are after is to make sure that when it's negative, it becomes positive. Hello. Hello. All right. How are we with time? We have half an hour left.
Yeah, 8:30.
So here is what I get out of my comparator from this triangle wave.
Next time, you know.
Yeah, that's why it's good we're not a TUI. Yeah, we're not. Although I think when they were cleaning the audience mixers, I've heard from Rich you could sell a bag of weed from that. You know, just what was you know underneath the faders. I guess people use it to skin up most.
Someone left a grinder in the back of the desk, didn't they?
Oh, as well, yeah.
And it got sent back. An audience sent an envelope with a grinder in it.
Oh, really? Well, there you go.
Yeah, I know I lost that.
Well, I studied in the Netherlands, so you imagine
You're allowed to do it there.
even worse. Yeah, of course. Yeah, do we have? I hope Ben is gonna give us an amazing sketch for. No?
I don't know. But when it sounded like I
It's not
wasn't
that
quite sure how it
complex.
went to the VCA. So I got a triangle wave going into the converter, less than zero, invert it, going to the VCA, and then the VCA there. But I wasn't sure how you took that.
Well, the thing is that we have to separate the two things, yeah? So we have to. That's. I wasn't quite meticulous in building it, but maybe it's worth giving it another try. So what we have is the triangle that goes into the comparator. Okay? Now this comparator gives me essentially a square type signal. Yeah? That's what we have there. So now what I'm trying to do is take this signal and invert it. Yeah? So this one went up, this one goes down. Yeah? And then take one VCA, take another VCA. This is now the CV signal, such that the triangle becomes the audio signal in both VCAs. But we now actually know that this particular VCA is actually just a multiplier, so it doesn't really matter which input you choose. I mean, we could actually test that with Audition. You know, just put in two high frequency signals, swap the inputs, and see whether it's the same thing, and it's likely to be. Yeah, and then what we expect is that here I get the top halves of the triangle. Here I will get the bottom halves of the triangle. Yeah. And then what I have to do is invert this one. So these go up, and then I can sum them together. And that should be my full wave rectified triangle. Is that cool? You can send it around if you guys want to see it in the back. Okay, so second attempt. The theory works, yeah? That's cool. It's understandable. So now let's see if I can build it. So we've got this. I think I've rushed it. That's the main reason why it didn't work. Okay, so we've got so far, we have this comparator signal. So let's take the actual triangle wave. So we keep looking at the triangle wave. Actually, I should probably set the trigger. Trigger source. No, oops, that's operation. Just a second. Set the trigger to first channel because the second one will be messy. Okay, so that's fixed now. Okay, so what I'm now gonna do is take that triangle. I have to double it as well later on, and take my comparator signal as well and take them through the CV. And this is okay, so that's that, and then oops, gonna have to. Oh, don't reach there! Bloody hell! Another one. Okay. Right. So this should be my top branch, yeah? And you see it's already messy. That's why the whole thing didn't quite work. So I have to make sure that here I get only the positive things. But this is quite puzzling because manual. Okay. The thing is, I might have to. Looks like my my comparator. What did it give me? It doesn't seem to have been a clean. Well, it is 0 and 10 volts. So it should technically mute the signal, but you see that's my problem here. So first of all, I'm inverting it for some reason. There it is. But then the negative part here is doing stupid things. Okay, does that? Okay. Looks like I can maybe tune it. Ah, right, there we are. You see, easy does it. There is still a bit of a glitch there, but let's say we want that. Okay, so that's one half of it, and then the other half of it should be the same triangle wave, but the inverted comparator output. Yeah, and there it is with the anomaly as well. Okay, so shall we try and offset that? Well, you imagine it being offset, okay? For now. Because I might be running, I should actually have the exact amount because I have 4 channels here. But yeah, so that's this. So now what we need to do is take one of these. So the first one. Okay, did I actually tune this one, or did I just, was I just happy with it? Let's see, make it a bit flatter. Here we go, it's a bit flatter. We still have this anomaly, but that's what it is, okay? So now I'm gonna take those 2 signals. So this is the first one, and the second one, and invert the second one. And that's the funny thing, that it's not quite inverting it. I have no idea. It looks like we have an issue here actually with the final summing. Okay, that's the positive one. See, there's something funny. It's almost like I don't even have this signal in there. But I've actually checked it. It was out of phase with this one, yeah? Or did I? Oh no, actually, yeah, that's not good yet. Huh? So this is the positive flank, but actually the negative flank should be running here, and my negative flank is also running there. So this is no good. It might be that my inversion is not quite right. That's the gap. So I'm afraid that, let's see. That's more like it. Yeah. Okay. Right, so now I have a negative part in there and the positive part in here. Okay. And now hopefully I can add the 2 together and invert one of them. And here we are. Yay! Okay, stretching the brains. I mean, obviously it's not a sound design course, yeah? Cool. Questions, ideas, anything you guys want to do? I think I have a few more things, potentially. Or shall we call it a day and get to the pub? Is your brains frying already?
Yeah.
Nicely?
What would be an application?
It's the wrong question. That's the thing we don't deal with. The application is make some noise in our experiment. The thing is that, you know, in terms of direct application, no man, no one will tell you this. I mean, there are electronics design books which go into full wave rectification from the 60s, 70s, and you did it with tubes, and you did it with transistors and all of these things. But in terms of what's the meaning of making a full wave rectifier out of 4 odd modules, I don't know. I think that the meaning is, you know, to understand it. You know, the understanding is the meaning, and you know, you develop an intuition for signal processing. That's the main thing. You know what to expect. You know, because actually, if you take it, you know, in terms of combinatorics, with such a system, well, this board has maybe 50 ins and 50 outs. So if you take the combinatorics of, you know, how many patches can there be made with 10 patch cables, that's a billion probably, yeah? So, you know, your intuition in terms of experimentation is really crucial. Because if you know, your basic understanding of synthesis, which I assume you guys have, you know, this is my synth voice, I filtered the oscillator. You know all these things that are available in a digital system, and you know how to combine them linearly. You know how they will make sense, you know. And the thing about digging this deep into modular is that, you know, you can come up with things that are just not available, you know, completely new things. And you know, the thing is that, I mean, personally I always deal with feedback loops, and I think one of the advanced courses will go into just feedback loops, because then I don't even have to think about it. You see, actually this I would not perform with, you know, 4 module based full rectification. There is no sense to that, yeah. But if I'm in the studio, if I'm doing funny things, and I'm like, oh, I want this snares to sound really weird, then I can come up with a lot of unorthodox patches that make snares sound weird, you know. And it's not, you know, it's not a fancy filter. It's nothing. It's nothing regular. It's nothing. You know, it is beyond. We're trying to go beyond what we're told to do, beyond what the designers of these things had in mind. And it's actually very easy already with 4 or 5 modules. You can go way beyond what they were meant to be doing. That's the idea here.
So you're saying that most people aren't doing that then?
Oh no. No. Well, I mean, no, definitely not. I mean, you can try. I think Russell Haswell is maybe one of the guys who is really getting into some experimental bits like that. But most people who use modular are making cool arpeggios and sequence drum rolls and things like that, you know. It's very rare that you actually get someone really stretching the kind of the possibility of the system. But as far as I'm concerned, it is a much more experimentally rich platform, you know, than any old thing, really. You know, and these are just basic electronics components here, but you know, you have modules with earth, like soil resistor, I don't know what they've done, like you have a little cabinet in there with soil, and it does something with current and the soil in there, you know. And then you could do things with light, you could do like light dependent resistors, you know. You have modules with skin conductance. You can put, I have in my drawer kind of a lie detector. I can easily put a lie detector in here, which is a funny thing. But the real interesting thing is where things really go chaotic. So I don't know, you guys were probably in this lecture last week or this week. So what happens is that if you build a system which is antagonistic in itself, you know, so you build a system which is pushing something, and then you build a limitation which is pushing it back, then you can get into things that actually you know, do their own thing. You know, you can go beyond design altogether. I mean, if you guys want, I can show you this principle. Do we have that amount of time? Yeah, we have 10 minutes, yeah? So let me just show you. I mean, we will go into details there. Obviously, we fried our brains with designing basic modules here. But I'll just briefly show you what happens if you do funny things with feedback. So this is my audio. So I'm gonna take one triangle wave. Yeah. Okay, so what I do now is I'm gonna send this triangle through a wave multiplier, which initially sounds like this. Well, we might as well be looking at this waveform now that we're here with the oscilloscope. So it's a kind of folded waveform, I expect. Yeah. So that's just that. And now I induce a feedback loop back around the thing. Okay, so I'm losing it a bit, but actually already with one wave folder and a feedback loop, you see, suddenly it's not behaving linearly, so I don't have this kind of up and down thing happening. Let's see if I can get... So the amount of feedback is quite crucial as well. Intermittency, yeah? That's already the basis of chaos there. I have a fully deterministic system, essentially one oscillator, one wave multiplier, and a feedback loop around it, and you get intermittent behavior already, yeah? So what's next? Well, I'll do the same thing. I'll take it through a filter and back into the mixer. Without the square wave, this feedback loop is doing this. And so that's where the, oh, sorry, without the triangle. With the triangle, I get this. Thing. Okay. Let's take this one. And then what you're supposed to get is points of bifurcation. normally I would be doing this through the compressor, yeah, and a high pass filter just to avoid DC offset. So you get a bit of more. Fairly rich sound, yeah. I can go on forever, obviously. my release now, they've released my tracks which I made like this, like solo chaos, and it's 8 hours on 6 cassettes. So you know, it's just a long form thing. Yeah, but ultimately, you see, I mean, for me, the most exciting things are these chaotic things which I'm not fully in control of, and you know, it gives me a lot of sense of, you know, sense of not being necessarily me who is doing it, which is exciting for me. But you know, if you want to make the craziest snare sounds in the world, what I'm saying is, you know the electronics, know the ins and outs of your modular, and you can do it. I mean, the kind of the options are much more endless than with the computer. You know, in many ways. So that's the purpose. That's the application. Cool, guys. Thanks for being so great.